Okay, I hope you can hear me all very clearly. I'm sharing my screen here, and I'm going to be your host today. A little bit about me before I get started, so I get acquainted with all of you. I am Emmanuel, and I'm from Rwanda, and I'm doing PhD here at the University of Oklahoma. Former co-chair of this JSA and your host today. GSC has been around for many years now, and we host a seminar regularly every week. And it's very, very important to us that you guys join us and come together. Some people have so many plans today, and there's so many uncertainties, including snowstorm, but you guys have chosen to be here, and you made the right choice because you'll never be able to hear this message we're going to hear today anywhere else. I would introduce the leadership committee, and we headed by Roshan and Rodney as co-chairs. And publicity is Razor, he's not here. Raj Mahan was also former chair. And Tarun, I believe Tarun is also here. I don't know his status, but Rachel is here. You can say hi.
Hello.
Can you hear me, guys?
Yes, proceed.
Can you hear me?
Yes.
We can hear you, but I think your video froze.
Oh boy. Hello.
We hear you.
Oh. Yeah, for some reason my Zoom just froze, and I think it warned me that my internet is very slow. So it's happening. Anyhow, I was introducing the committee, and I think I was on Rachel. She's here. On support, myself, I represent the GSC to the Graduate Student Senate, and Anuriban is our treasurer, and we have Robert, and most importantly, our mentor, Farouk Mistry, who is here to support us, and we appreciate to be with him all the time. We meet regularly on Friday at 4 p.m. So feel free to join. We're gonna send out the invitation to regular meetings. You are welcome to join our regular meetings. So if you're not a member, take your time to either copy the link on the slides or scan the QR code using your mobile app camera, your phone camera on the screen. I'll wait for a little bit before I proceed. And it's very important to us that you become a member of JC. And Rodney, if you have any question about membership and anything, you can reach out to Rodney or Roshan. They will give you a thorough explanation on becoming a member and all the benefits that members enjoy. With that, I think I gave you enough seconds to scan the QR or copy the link. I'll move forward. We have, you can check our Facebook page and YouTube channel. You can see the recent videos or the videos from the past. We're going to have the seminar next week with Greg Marco, I can say his name. And we're gonna show a person that say hi to you guys. She's going to be, I'm not going to ruin it. I'll just let it like that. So you guys have to attend to find out what she has for us. With that, I'm going to introduce the speaker today, and he's talking from Australia. He's a PhD candidate from the University of Melbourne. And before I say anything, I would like to say thank you for talking to us. So thank you for giving us this presentation. Having to wake up at 4 a.m. and attend the seminar series, it's something heroic, and we appreciate you so much. I know Jean-Pierre for a long time. We grew up in the same town. We went to the same elementary school. We shared a lot of memories together. And when I was growing up, it was very hard to have mobile service. And it was every child's dream to make a change to that particular area. Jean-Pierre has grown in that area, in that country that was not developed so much, to set the bar so high, to set the standard, to pursue the excellence that we see him today as a university student. He set the bar so high that I was always chasing to get to that goal, being always in the mind to be like him. I'm not sure if you guys can still hear me. Okay, I think Ronnie can hear me, and Rachel. Most people don't have video, but yeah, what I was saying, that it's very inspiring to me and everyone that is here, having the background such as mine, such as Jean-Pierre, such as everyone else, to have a breakthrough and pursue the goal that people would appreciate. And he took that challenge to join the University of Rwanda, where he graduated with great distinction, and he was he moved on to pursue his master's at the University of Halim. It's in South Korea, am I right? South Korea. And from there, he went on to do his PhD at the University of Melbourne, where he is right now. I was speaking with him one day when I was doubting if I should go to graduate school. I was in my senior year, and I asked him, "Why are you doing PhD?" And he gave me the simple answer: because it's the right thing to do. And it's that moment I realized it's worth my time, it's worth my energy, it's worth my thoughts to do the same. So with that, I was always inspired by him.
I think you are going in and out. I think it's time to have the speaker talk.
Yeah, so please, faculty and the students, members of the GS committee, please welcome Jean-Pierre Ndawakuranye from the University of Melbourne.
Stop sharing so Jean-Pierre can. Thank you.
Do you guys see my screen?
Not yet.
Uh-oh.
I see it.
I can see it.
Yeah, I can see it.
All right, so actually I will, because I'm using a bigger screen, I will switch off my video here so that I can concentrate on the bigger screen. I hope that doesn't bother you a lot. Hi, thanks Emmanuel for kind introduction. Thank you, our team, for allowing me to present to you today. And my presentation will be about point of care bilirubin monitoring. And as Emmanuel mentioned, I'm from the University of Melbourne, Australia, School of Physics. And my supervisors have Aman, Mike, and Stephen. Those are the people we work closely together in every day-to-day work. So, first of all, as Emmanuel mentioned, I moved from Kigali in 2014, went to South Korea for my master's there. And in 2017, I moved to Australia. And from there, I've been working with my team. These are the people that I work with day to day. This is the whole team of carbon cybernetics. This is when I was confirming my candidacy after 1 year of my PhD. So my presentation is going pretty much to be about it's going to be a non-technical discussion, I would say, because I don't want to be boring you, because we all have different backgrounds, so I don't want to go into the technicals. I will try to talk to be a sort of a storyteller. And if you have any questions along the way, please feel free to interrupt, because I like being interrupted. It's sort of a conversation anyways. So first of all, why am I doing this? Because there should be a motivation. We all know that the previous years, in recent years, there have been different technologies evolving, pretty much sort of having wearable sensors, we have implantable sensors, we have handheld devices, we can have those home care tests, we can have glucose home tests. All these things combined together told me, hey, there's something you can work probably to improve the health of people with liver disease. So the first motivation was the technology that has been evolving in the recent years. The second motivation is pretty much the disease. So we have a disease, pretty much liver cirrhosis. We probably all know that when babies are born, before the liver kicks in, their skin is yellow because the liver is not able to filter blood to take the toxins out. So they put them under blue light in the treatment called phototherapy. So, and the way they normally measure the levels of bilirubin in blood, they use these handheld devices. And the reason they do that, I'll probably go into that later, is because the skin of babies or infants is it's somehow transparent, so they can measure in vivo bilirubin using this optical method. So So to just go a little bit deeper, bilirubin is obtained from the heme catabolism. Heme catabolism is that process whereby red blood cells die. After like 120 days, they die, and they dissociate. Some parts become hemoglobin, and hemoglobin also dissociate into heme and globin. Globin is pretty much that part that has iron in it. Then heme goes on to become, I'm not gonna go into the details here, but it will go into a number of steps where it can become bilirubin. But this bilirubin is the form of unconjugated. This unconjugated bilirubin has to pass through the liver to be conjugated. This unconjugated bilirubin is water insoluble, so it does not dissolve in the blood. It takes on albumin, then albumin can take it through blood to the liver, and through the liver, that's where unconjugation takes place. Then the conjugation taking place in the liver, then unconjugated bilirubin becomes conjugated bilirubin. This conjugated bilirubin can dissolve in the blood and can be transferred to the kidneys or to the bone and excreted out of the body. So that's pretty much the whole process of heme catabolism. That's how the body gets rid of bilirubin. So I just explained that one, but various conditions or like viruses, bacteria, or excessive alcohol intake might cause liver damage. And you understand if the liver damage is damaged, you will not be able to conjugate bilirubin. So if bilirubin is not conjugated, if the UCB is not conjugated, it will be, its level is going to increase in the blood. So pretty much to show you what happens if the liver is damaged, sort of there will be, as I would say, a secondary path where the toxins will be dumped in the main circulation. You have a lot of toxins in the blood increasing. So that's a problem because the liver is not functioning well. And this condition has, WHO has recorded around 1.5 million deaths per annum. That was reported in 2018. So that's not a good thing. But the way people do it in clinical settings, once a patient is after diagnosis, patients are required to attend the clinical visits where they have to go through all health assessment. And what they do, they take up blood and urine, and they will measure how much blood takes to coagulate, take bilirubin and creatinine contents. So all these parameters are taken and put in one score, then you can determine how bad is your liver health. But as you understand, people have to go to the hospital and come back home, but their health can deteriorate. And some people have, some research have demonstrated that bilirubin alone, not all of the three parameters, just bilirubin can be used as a biomarker. So you can use bilirubin alone to determine liver health. So there are different bilirubinometric techniques. Have spectrophotometry, there are optical, have chemical, chromatography, there are other many techniques. But most of these techniques have limitations of complexity. You might find like it's a big system on the benchtop in the hospital, so they require people to, with expertise to operate them. And you understand this takes time because people have to leave home, go to the hospital, come back home. And these systems are really expensive. Other techniques that you have seen earlier called transcutaneous, this one, transcutaneous. So these have problems because when people become adults, their skin thickness increases. And the content, like for instance, the amount of melanin lipids will increase. So this technique cannot work. So the idea is either you just get a handheld device that can be used as a glucose meter, or you just get an implantable sensor. So to supplement the existing technology, I'm not claiming that this can sort of change the whole game, but it can also add in to the existing technology. So the method that I'm using here is, this is like one chapter. I didn't mention that. This is like one chapter that I'm sort of looking into, but I will not go deeper to other chapters that I worked on because it would be too long and probably too boring. So you probably all know about Beer's law, where there is light and it's sort of absorbed, that we can measure the absorbance. So normally going a little bit deeper into the technicals of this method, so we have a light coming in, a light coming out, so we can measure the absorbance of the sample using this formula. So for instance, if you have this light intensity coming in and light intensity coming in, and to measure the intensity out, you can use this formula of I is equal to I naught times 10 or epsilon T times C. So epsilon is like the extinction coefficient, and T is the path length of the sample, and C is the concentration. But there's a very easy method where you can, instead of using this very complicated system, you can actually use two wavelengths. Instead of using a sample and a reference sample, you can use two wavelengths, and one wavelength is going to act as the reference itself. So that's good because you don't need a reference solution, and this is going to be easy because, but one problem that this has is because you have to make sure you select a wavelength according to the substance you want to detect. In this case, we are talking about bilirubin, and I'll probably go deeper into that now. So one thing that we had to do was to select those two wavelengths, because it's really important to find those two wavelengths. It's work to be done, because if you want to detect another substance, then you have to find another wavelength. In this case, I wanted to look into how can I get those two wavelengths for bilirubin. First of all, you look at its optical absorption spectrum. When you look at it, its absorption optical activity is highest in the blue wavelength. And that's not a surprise, because we have already seen that people in the clinical settings, they use blue light for phototherapy. Also, because bilirubin is in blood, I was trying also to compare it with other blood pigments. And one most important thing you must know is that in blood, we have hemoglobin. Hemoglobin is, I would say, the major light absorbent. It's the main absorbing chromophore in blood. So when you see blood and it's red, you know that color is due to the fact that you have an enormous amount of hemoglobin in there. So talking about hemoglobin, I think it's just blood. If you look at, this is oxidized hemoglobin, or I would say oxygenated blood, we can call it that way, or deoxygenated blood. So they have different, I would say, different optical absorption spectrum. But of course, like here, I try to use 98% of saturation, which means we are looking at the normal saturation the normal oxygen saturation of blood. So, but when you look at both, you realize you have a small window between 450 and 480 around there. where bilirubin has higher extinction than blood itself. So we have to be able to, and one thing that is more important is that you also have to remember that bilirubin at that particular wavelength, that's where bilirubin absorbs more. So that's good because bilirubin has higher than blood, but also it has the highest, it's the highest point. So that's good. And as we try to compare this, I try to put them on the same scale, but you realize that at that specific point, around 470, that's where if you take the ratio of bilirubin extinction coefficient and you divide by the extinction coefficient for blood, you realize that ratio will peak. The peak will be around 470 nanometer. So that's the main point that we have to take as the analytical wavelength. So as I didn't probably mention that you have to take two wavelengths. One wavelength has to be the analytical. From one case is that you have to consider analytical wavelength where the substance absorbs highest. And another reference wavelength is where the substance you want to detect absorbs less. So we look for another wavelength around 525. The reason we took that is because, first of all, bilirubin absorbs almost less, I would say less. If I say absorbs nothing, I would probably be wrong, but it absorbs less. And also, if you look at it, it's called isoabsorption point. So when the oxygen saturation changes, this point does not change. So will still be a fixed point. So the oxygen saturation will never change this point. So that's good. That's why we choose also 5 to 5. So we have been able to choose the first feature, that is the wavelength, 470 as analytical and 525 as reference. So another thing was to look at the concentration range. The concentration range, because you have to be able to look at the concentration for cirrhotic patients, and looking at the literature, I realized that the levels in cirrhotic patients can go up to 30 milligrams per deciliter. It can also go higher, but I decided to work on this range. So you have to be more careful about this range because you don't want to work on maybe 100 milligrams per deciliter. You also don't want to work in the range of less than 1 because we want to be targeting initial motivation, which is cirrhotic patients. So we also have to be able to get a reasonable light path length because we want to be able to get a good signal, I would say, a good optical signal. So we tried too many path lengths, and we realized around 200 micron path length is the, because blood really absorbs a lot. So we'll have to go down, absorbs a lot, mostly in this range, in the visible range. But if you go to beyond 600, the absorbance reduces, but this area of visible, you can see the absorbance is really, really very high. So have to go down the path lengths below 250. And you can see that after doing some measurement on blood, we realize that we can get a good signal. And the good signal we have to have is that we have to have a good signal at 470 nanometer and 525 at these 2 points, because those are the, this point is the analytical point, and this is the reference point. And one thing that we had to do is to make sure that we really have blood, and the way you test that, to validate that the sample you have is blood, is to look at these two peaks. So you see we have 2 peaks for oxygenated blood. So that's very, very important. So I don't think this is more technical, I would say. So just prepare solutions for bilirubin alone, and we try to see if actually 200 millimeter or 0.2 millimeter or 200 microns path length is enough for our measurement. We measured, and you can see the linearity is astounding. So two things that we had to do. The first thing was to look at, actually, can we be able to detect bilirubin in blood phantoms? So we went out, bought commercial blood, and we tried to prepare solutions for blood, and we went ahead and measured bilirubin, because there is no other easy way to test bilirubin in blood other than getting bilirubin, putting it in blood phantoms, and testing it or detecting it. So this was pretty much my first setup. I did not want to picture the image because it had too many wires, so it looked very messy. But pretty much this is how it looked. But first, I used a normal dark acquisition or digital multimeter. So it was sort of manual. So I was using manual to detect the signal. So I had a multi wavelength light source, had blue and green. So, and pass through the sample and detect, and now use it to find this error, the ratio of the log of V sense voltage for blue and the sense voltage for green. And that's what I said actually here. That's what I said here. So then after that, I tried to look at how does this ratio change with the concentration. And you can see we had a very, not very, I would say, but the linearity between the absorbance ratio and the concentration was not very bad, I would say. But again, what I should also mention is I used two methods. One method was to use the dual wavelength. The dual wavelength means working on the system. Another is the spectrophotometry. The spectrophotometry is I just took my sample to the UV spectrophotometer and measured the full range absorption spectrum and picked the absorbance values, extracted the absorbance values, and found the ratio. So that's this is pretty much like how they would do it in the hospitals, but this is how I would do it on a benchtop or in the system that I would take at home. So that was one for the blood phantoms. And basically, blood phantoms are more or less hemoglobin. So that was not enough. And I said, oh no, why don't I now choose real blood? So I went out to the amateur, got porcine blood. And but now again, what other thing that I wanted to do, I was going to do more something that can be controlled. And this time I used the microcontroller to control my system, not manually, but this time I used a sort of a microcontroller to do all the measurement. But a few things that I had to mention also are probably the concentration was up to 30 milligram per deciliter as I did for phantoms. I also did both dual wavelengths and spectrophotometry. We had to choose some anticoagulants. Also this time, because as I mentioned earlier, bilirubin will degrade on blue light. So you have to make sure you choose really small or short pulses, because if you choose like 2 seconds, you might be degrading bilirubin instead of measuring it. So it's really important to be able to choose the right on and off times. Also irradiance, because you have to be sure that you don't get like 10 milliwatts or I mean, like if you choose like 20 milliwatts per centimeter squared, you're probably degrading bilirubin instead of measuring it. So you have to choose a very small, I would say, so the reason we chose porcine blood is because it was, I would say, affordable, and also it's a better estimation of human blood, because if you look at the aggregate in red blood cells, you can compare. It's comparable to human blood, and also human blood, you know, it's not easy to get. And if you want to get human blood, probably going to have some more ethical procedures, and it's a lot of trouble. So we had like to wait for like 6 months to get ethics and get PC tool up, all this kind of stuff. It wasn't an easy task, so we decided to go for porcine blood. So I was talking about this system. The main thing is that it was more or less controlled, and using a microcontroller, you can still have an algorithm. So I don't think it's, yeah, I don't think there's much that I can say here, but again, this was more controllable. You can see it's a system out there, and you can control it using microcontrollers. I also did some analysis using the absorbance ratio. So I call it apparent absorbance ratio because it's not like real absorbance. It's just the ratio of the logarithms of the V sense or the voltage sense. I mean, of the sense voltages from the microcontroller, from the current in, from the photocurrent. So there is a photocurrent here that you pass it through a resistor, and you can measure the voltage across that resistor, which is the voltage, the sense voltage. So I also did this measurement and tried to compare the ratio with the concentration, and the linearity is not bad as well. But one thing you should realize is that it's not really easy to determine, to make a distinction at low concentrations. Maybe below 3, you cannot easily distinguish between these values. But at higher, maybe somewhere at 5 or higher, you can, the accuracy is higher at higher concentrations of bilirubin. And that's critical because for cirrhotic patients, these concentrations are more critical. From maybe around 3.5 or 4, that's where cirrhosis, those are, I would say, those are the concentrations that represent cirrhosis. So we are not much interested in the normal range. We are more interested in the cirrhotic range. So that's good because the interest is not at lower concentration. Of course, this can be improved. That's what we are doing currently. I'm not going to go into the details, but yeah, we are trying to improve the accuracy and the precision for the measurement. So in this first chapter, actually, this is like my chapter, or my first chapter of the results. We have 3 of them. The first thing we did was to choose the features. So we have to have path length, concentration, operating wavelength, and all these features. We also had to see if bilirubin obeys Beer's law. By Beer's law, I mean the linearity. We just want to make sure if we had the concentration of bilirubin on this cirrhotic range from 0 up to 30 milligrams, and we expect the linearity. We found out that it was indeed. Another thing was to determine the sensitivity of bilirubin in the blood, this time in phantoms, blood phantoms. Another thing was to look at the sensitivity of blood in whole blood, of bilirubin in whole blood, and we did that too. So the results were, we determined 470 and 525 as the wavelength. Path length was determined at below 250 microns, and the concentration range was determined to 30 milligrams per deciliter. And overall, the coefficient of determination was over 95% for both in phantoms and animals, and for full range and wavelength. But of course, full range had shown a higher accuracy, not really extremely higher, but there is some sort of differences, and you understand, because that's a big system, it has higher resolution and all that kind of stuff. So it's not very surprising to find out that the full range spectrophotometry has a higher accuracy than your wavelength. But of course, as I mentioned, we are trying to get a higher accuracy for the measurement. So things that we have to know also, your wavelengths is simple, makes things rapid, because you can measure it at home. And this is actually simple. Maybe you can design a device of maybe less than $50 and take it at home, measure your blood bilirubin levels at any time you want. And the good thing is selectivity. Selectivity means you can measure bilirubin. You target bilirubin and you measure it alone, not other substances. Another thing is the temporal evolution. This is actually also important. I didn't mention that, but it's important because what is important in cirrhosis patients is not just the concentration of bilirubin. It's also how does bilirubin concentration increase day to day. So if you had maybe 2, tomorrow is 3 milligrams per deciliter, another day is maybe 5, that information is also important. And with the current technology, unless you live in the hospital, it's impossible to get that information. So, as I mentioned, I have 3 chapters. The second chapter should be to use bilirubin degradation profiles to find its concentration as ongoing. We're also thinking of using electrochemical methods for bilirubin monitoring as well. And we are thinking of using diamond electrodes. And you understand, because we are in the carbon cybernetics group, so diamond is the main focus of our group. We make diamonds in my group. So this is the people that I work with. Aman is my supervisor. The one I work with, he moved recently to MIT, where we are still together. Mike is in China right now, working with Hawaii Technologies. Stephen is still at Melbourne Uni. He's our main guy, the head of the group. These are the people that these are the institutions that I've been working with, experiments. Melbourne Uni, definitely. Murdoch Children Research Institute. They have a project on bilirubin for babies. I work with them. And Diamond Valley is the place that I procure the blood from, and have Melbourne Center for Learning Publication. So a government institute that helps university research, and this is Aman works. So these are the people I work with. We're on a trip on Phillip Island, somewhere in South Australia. So I'm happy to hear your comments and probably your suggestions. If you think there's something that I can improve on, happy to look into that. Thank you very much.
Thank you, Jean-Pierre. Everybody, please join me to thank Jean-Pierre for a wonderful talk. You can say there's an icon for the hand thing. Thank you, Jean-Pierre. So I will open the floor for questions. I will take questions first from the students, then the faculty. If any student has a question, please. Faculty. I see, no. I still have no questions.
So I know that with severe liver disease, you can have other problems such as yellowing of the eyes. Is there some way you can examine for bilirubin without actually, taking a sample of blood?
Oh, well, I didn't think about the eye, but we also thought about, because one thing that I was doing was to determine which points on the body that can be best for the detection. I didn't think about the eye itself, maybe using some sort of optical method like detect on the eye. But we're thinking different positions. One point was I think this is sclera, but of course it has skin. So any place that has a skin, you either take blood out or you put an implant in. So that was our focus. I mean, the implant probably is going to come maybe after my PhD. I'm not thinking of doing an implant right now because I don't think I have enough time. But well, I might actually, I will think about that option as well. Maybe it's possible to detect blood, bilirubin in the eye. But one issue that is there is no, I would say there is no fixed point where you are, say, at this concentration, the yellowing of the eye will take place, or the yellowing of the skin. So it's I would say it's relative. It depends on one person, from one person to another. So that's that one. That is the only issue I would say.
Okay, thank you.
Thank you, Dr. Ellen. Anyone else has a question?
Hi, Jean-Pierre. It's really nice of you to participate at 5 a.m. in the morning. Now it's 6 a.m. in the morning in Melbourne. I have a question that is sort of tangentially related to what you talked about. Based on what you've done or what you will be doing, how many people do you think will benefit from this, just say in Australia? Is it a big problem, small problem? What is it?
Well, actually, I got that question from the people because we are thinking of getting an IP for the project and doing some patent procedures. But they asked me that question. But the idea is, in Australia, there are people who live in the country because they take, mostly the Aboriginals. So they take long to come to the hospital. They don't have the access to, like Australia is, I'm not sure about the US, but it's like you have Melbourne, the whole Victoria. Other than that, nothing else. It's just country. You have South Australia, it's Adelaide, and others are like countryside. So those people in the countryside would benefit a lot from this. But also I was thinking about people in countries like South Asia or maybe in Africa as well, people who live in remote areas. So that would be beneficial to most of those ones. But if you look at demographics of Australia, I would say maybe around 2 million, if that's a guess estimate, but we are looking at people who live in areas that don't have access to. Yep.
So let me tell you why I asked that question. See, to what extent will you be able to automate the system? To what extent will you be able to use the internet to use, because what you're really dealing with is diagnosis and then treatment. So to what extent would you be able to use the digitally transforming world or the opportunities we now have because of digitization to deal with this telemedicine type of thing?
So one thing, actually, I'm also writing a review paper about that. So one part is to suggest maybe how do people have sort of how do people use this? Like, and as you mentioned, it's more about diagnosis, it's not a treatment. But what happens is you might think about this in terms of, hey, everyone has a mobile phone, and probably you can download a sort of mobile app, and once you do the measurement, it goes directly to the app. Maybe that information can be sent to the doctor via an SMS. I think that it doesn't require a lot of technology there. You just have to have a mobile phone and the device, and you should be good to go. But that's like the basic idea. We might also think other ideas as the project progresses.
Well,
yeah,
we have Rachel here, who is dealing with a similar sort of issue on pregnant women. So Rachel, maybe you'd like to share some of what you're doing with everybody, your preeclampsia and eclampsia in women, and how you're tackling the problem.
Which particular part of the problem? Sorry?
How you're tackling, first, what your problem is and how you're tackling it, and what the nexus is with what Jean-Pierre talked about. Because while he was talking, I was thinking of you.
Oh. Well, I'm researching how to use machine learning to predict preeclampsia in women. And it's kind of a tricky problem because it's a very imbalanced kind of problem. The majority of data sets involving pregnant women doesn't have preeclampsia. And so most machine learning models tend to overlook those women. So I'm trying to change the models to kind of better detect it. So I guess that's kind of similar. I apologize. I kind of lost a little bit of internet in the middle, but.
So let me tell you where she's coming from. She's got a data set, and she's using machine learning to predict which set of women will have this disease when they're pregnant. Okay. So my next question comes up then and says, could you do something similar to that? That means collect data from around the world, whatever data is needed, or could you identify the data that is needed so that prediction could be based on using these machine learning techniques?
Oh, that was for me?
Yeah, that's the question for you. So instead of doing experiments, you would look at the data and say, yes, this person fits into this category, or this person fits into this category, after the person has used the mobile phone to do whatever has to be done.
Yeah, I think, I'm not really into the machine learning a lot. So I'm more into optics and, doing optics experiments and getting data from there and try to get some information from there. But I think that's something probably that I should look into as well. But when that requires some sort of interconnectivity between people with that disease as well, because maybe some people might want their health to be, I would say, a secret, because people normally don't want to share that information, or maybe they can share the information in a blind way that doesn't tell the name. Or I'm happy to look into that and probably have.
But it's just an idea for you to think about in terms of, after you've done your work, how you can expand it, how you can bring it to the market. And in Rachel's case, she's got all this data. However it's collected is a different story. She's got this data. She doesn't know who the people are. But then if one person goes to it, then guess what? You look through this database and say, you have the symptoms. Okay, now we are going to check you out and stuff like that. So it's a predictive diagnostic tool that you are likely to get it. And that's what I think you're looking for here.
Also, if I remember, it's been a while since I thought about this. I think it might also be useful for babies that are born with Rh incompatibility. So you might think about that too.
RH?
RH.
RH negative.
Yeah, the blood factor, RH negative, RH positive.
Oh, RH. Okay.
But that would be something you'd need fairly rapid assessment for, because babies don't have a lot of, time to wait around while you do things.
Yeah, I agree.
So your work, all I'm saying is that your work is kind of interesting because it can go in many different ways, and it's quite exciting. And perhaps you, Rachel, and you can talk a little bit and share some ideas, because I see a nexus between the two, not between exactly what she's doing, but the way in which she's tackling this problem, and the problem that you're tackling is the same. You're trying to predict. Anyway, so back to you, Emmanuel.
Yeah, thank you so much for everyone's contribution. This is the purpose. It's the purpose of this conversation, this meeting, that we share insights and get insight from other people, and we build onto that to come up with research ideas. We are joined by very important people. I'm gonna mention a few. Thank you, Dr. Ellen, for being here with us. And we have Dr. Kesimpo here with us as well. Thank you very much for supporting us, being here with us. It's very important to us and we appreciate it. And I noticed Andrew is a guest. I believe we never met. Andrew, are you there?
Yeah, I am.
Yeah. Yeah, thank you very much for supporting us. Your presence is very appreciated.
Thank you.
And I would like to Professor Rathi, joining us to join, and his presence here with us is very appreciated. So please welcome Dr. Professor Rathi.
Thank you. Nice presentation, Jean-Pierre. We use a similar technique in flames to measure soot volume concentration. So I am familiar with the application of Beer's law. So we use a laser beam and look at the absorption as it passes through the flame, look at the intensity ratio in order to determine the soot volume concentration in the flame. So that was very interesting to see how you applied a similar technique in order to determine the bilirubin concentration.
Hello.
Hi, how are you?
Yeah.
All right, I need to go for another meeting, so I enjoyed the lecture. Thank you. Bye.
So I have an announcement. On the 25th of February, we are going to have 3 people present lightning talks at the ASME local chapter meeting. I'll be sending information out to everybody. Emmanuel is one of them, Rachel is another one of them, and Roshan is going to be the moderator or the synthesizer for that session. So it's at 6 p.m. Local time. So we hope that you'll be able to tune in and cheer our folks when they make their presentations.
Yeah.
Emmanuel, back to you.
So thank you very much, Dr. Professor Rathi. I know you have to go. I would like to hand over my hosting to Roshan and Rodney. And this is where I say goodbye to all of you. I will stick around to hear their closing statements. So either Roshan or Rodney, I would like to hand over the microphone and you can welcome Dr. Mistry to say a closing statement as we adjourn.
Okay, hi again, everyone. That was a nice presentation. Thank you again. The only other thing I have is that we would love to see everyone at our meeting on Friday. You're always welcome. Bring yourself, your input, whatever you want to say, and check out our YouTube channel for other great seminars that we've had. Roshan or Farouk?
It's been simply delightful to have you join us, Jean-Pierre from Melbourne. Janet and I spent 7 years in Australia. We were in Sydney. And in 2018, I drove across the country from Sydney, across the Nullarbor, that's Kalgoorlie and all those, across the Nullarbor plains through Kalgoorlie to Perth. So I'm familiar with Australia and the sort of landscape that you're talking about. I've been to Melbourne several times. I spent quite a bit of time visiting Adelaide, the shipyard at Adelaide. And one of the things I enjoyed very much in Australia was the wine, the Penfield wines, winery and stuff like that. Yeah. I don't drink anymore, but but in those days I did enjoy wine, and we still have a bottle that we brought back with us in 1981, and it's in our wine rack.
Probably not any good anymore.
That's a memory. Yeah.
Okay, so thank you all very much, and.